every way humans could travel to the stars. Space is complicated. We make it simple. The nearest star system to our own is 4.2 light years away. That number sounds small until you convert it into anything a human engineering project can actually work with. At the speed of our fastest current spacecraft, the trip would take roughly 75,000 years. Every proposal on this list exists purely to attack that one brutal number, and none of them get there easily. We're going in order from what we could technically build today to what still lives entirely in the realm of theoretical physics, then we'll sort them a second way by how long the actual trip would take. Because on this list, a working propulsion concept and a trip a human being could survive experiencing are two very different bars to clear. Chemical rockets. We begin with the only method humanity has actually used to leave Earth so far, and also, bluntly, the one least suited to the job on this list. Chemical rockets work by burning propellant and expelling the resulting hot gas out the back at high speed, and they remain, even after decades of refinement, fundamentally limited by something called the rocket equation. The faster you want to go, the exponentially more propellant you need to carry, and at a certain point, the extra fuel weighs so much that adding more of it stops helping at all. Here's the fact that should genuinely bother you. Even with a theoretically perfect chemical rocket, carrying nothing but propellant and a payload, reaching even 10% of the speed of light is essentially physically impossible using this method, because the exhaust velocity of the best chemical propellants tops out at only a few kilometers per second, hopelessly small compared to the roughly 300,000 kilometers per second that light itself travels. Chemical rockets got humanity to the moon and are currently getting robotic probes to the edges of the solar system. They are not, under any realistic scenario, a method that will ever get a human being to another star system within one human lifetime. Gravitational assists. Here's a method worth understanding before we go further, because it isn't a propulsion system at all. It's a way of stealing speed for free. A gravitational assist, sometimes called a slingshot maneuver, uses a planet's own gravity and orbital motion to accelerate a passing spacecraft, borrowing a tiny, almost immeasurable fraction of that planet's momentum in the process. Voyager 1 and Voyager 2 launched in 1977 and still transmitting from interstellar space today used a rare planetary alignment to chain multiple gravitational assists off Jupiter, Saturn, and beyond, achieving speeds no chemical rocket alone could have provided with the fuel they were actually carrying. Here's the fact that should genuinely bother you about the limits of this trick. Even after every available gravitational assist, both Voyager probes are traveling at only about 1/600th of 1% of the speed of light, enough to become the first human-made objects to leave the solar system, and still slow enough that reaching even the nearest star, which neither Voyager is aimed at, would take on the order of 70,000 years. Gravitational assists are free, clever, and have already taken humanity farther than anything else on this list. They are also nowhere close to fast enough to solve the actual problem. Ion and electric propulsion. Here's the twist. The solution to interstellar travel might not be more thrust. It might be patience. Ion engines work by electrically accelerating charged particles, usually xenon gas, out the back of the spacecraft at extremely high exhaust velocities, far faster than any chemical rocket, but producing a comparatively tiny amount of thrust at any given instant, often no more force than the weight of a single sheet of paper resting in your hand. Here's the fact that changes everything about how this technology actually works, because that tiny thrust can be sustained continuously for months or years. Rather than burning out in minutes like a chemical rocket, an ion-powered spacecraft can eventually reach far higher total speeds than a chemical rocket ever could, simply by patiently accelerating for a much longer time. NASA's Dawn spacecraft, powered by ion propulsion, used this method to visit two separate distant objects in the asteroid belt during a single extended mission, something no chemically fueled probe carrying a comparable amount of propellant could have managed. Here's the part that lingers. Even at its theoretical best, ion propulsion still tops out at speeds representing a small fraction of 1% of light speed, genuinely revolutionary for exploring our own solar system, and still nowhere near sufficient for a crewed interstellar mission on any timescale shorter than tens of thousands of years. Nuclear thermal and nuclear pulse propulsion. Here's the reframe. To meaningfully close the gap, you need an energy source dramatically more concentrated than chemical combustion, and nuclear reactions are, by a massive margin, the most energy dense process humanity currently knows how to control. Nuclear thermal propulsion uses a nuclear reactor to superheat propellant before expelling it, achieving significantly better performance than chemical rockets, and has actually been ground tested by both American and Soviet space programs, though never flown on an operational mission. A far more radical version, called nuclear pulse propulsion and studied seriously in a 1958 to 1965 American research effort called Project Orion, proposed detonating a series of small nuclear explosives behind a heavily shielded pusher plate, essentially riding a controlled sequence of nuclear blasts one after another to accelerate a genuinely massive spacecraft to a meaningful fraction of light speed. Here's the fact that should genuinely bother you. Project Orion's engineers calculated with real seriousness that this method could theoretically send a spacecraft the size of a small city to a nearby star system within a single human lifetime, using technology that existed, at least in component form, in the 1960s. It was never built, primarily due to the 1963 Partial Nuclear Test Ban Treaty prohibiting nuclear detonations in space and the deeply unsettling logistics of launching thousands of nuclear devices from Earth's surface in the first place. The most physically plausible interstellar propulsion method available to mid 20th century engineering was abandoned not because the physics didn't work, but because the politics understandably could never allow it. Nuclear fusion propulsion. Here's the pivot. If fission based nuclear pulse propulsion is politically radioactive in every sense of the word, fusion offers a theoretically cleaner path to the same destination. Fusion propulsion would generate thrust by triggering the same nuclear reaction that powers the sun itself, releasing enormously more energy per unit of fuel mass than fission without producing the same volume of dangerous, long lived radioactive waste. Project Daedalus, a detailed engineering study conducted by the British Interplanetary Society in the 1970s, designed a theoretical fusion powered probe capable of reaching roughly 12% of the speed of light, which would put a one-way trip to a nearby star system at around 50 years long, but genuinely within range of a single dedicated human career, if not quite a full round trip lifetime. Here's the fact that should genuinely bother you. Humanity still hasn't achieved sustained net positive nuclear fusion for power generation on Earth, let alone miniaturized and weaponized it for propulsion. Every fusion propulsion concept remains fundamentally blocked behind an engineering milestone we have been chasing, with only partial recent success since the 1950s. The propulsion method that offers the most realistic looking path to a nearby star within a human lifetime is currently waiting on a breakthrough we don't have a confirmed timeline for at all. Antimatter propulsion. Here's the fact that reframes the entire scale of this category: antimatter annihilation. When matter and antimatter meet and convert their entire mass directly into energy, is, by a massive margin, the most energy dense reaction physically possible under known physics, releasing roughly 1,000 times more energy per unit of mass than nuclear fusion. A spacecraft powered by even a small quantity of antimatter could theoretically reach a meaningful fraction of the speed of light with dramatically less fuel mass than any nuclear method. Here's the fact that should genuinely bother you. Antimatter is, by a staggering margin, the most expensive material humanity has ever produced. Current particle accelerator facilities generate antimatter in quantities measured in nanograms at a cost that has been estimated by some physicists at trillions of dollars per gram, meaning the entire global supply of laboratory produced antimatter accumulated across the entire history of particle physics research wouldn't be enough to power a light bulb for more than a few minutes, let alone propel a spacecraft to another star. The physics of antimatter propulsion is, in principle, completely sound. The economics of actually acquiring enough of it remain somewhere between the greatest engineering challenge in history and not currently possible at any price. Beam propulsion and the solar sail. Here's the twist that flips the entire strategy. What if the spacecraft didn't carry its own fuel at all? Breakthrough Starshot, a research initiative announced in 2016 with backing from prominent physicists and private funding, proposes launching a fleet of gram-scale probes attached to thin, reflective sails, then accelerating them using an enormous ground-based laser array focused on Earth, pushing each tiny probe up to roughly 20% of the speed of light within just a few minutes of laser exposure. At that speed, a probe could reach the nearest star system, Alpha Centauri, in a little over 20 years, dramatically faster than any propulsion method carried aboard the spacecraft itself. Here's the fact that should genuinely bother you. The concept only works because the payload is deliberately tiny, a probe weighing about as much as a paperclip, since accelerating anything larger, let alone a spacecraft big enough to carry human beings and life support, would require a laser array of an entirely different, currently unbuildable scale. Beamed propulsion may represent the most realistic path for sending a scientific probe carrying cameras and instruments to another star system within this century. It offers essentially no plausible path for sending a person. The Alcubierre warp drive. Here's the fact that closes this list on its most theoretical, most misunderstood note. In 1994, physicist Miguel Alcubierre proposed a genuine, mathematically valid solution within general relativity that would allow a spacecraft to travel effectively faster than light, not by moving through space faster than light itself, which remains strictly forbidden, but by contracting space-time in front of the ship and expanding it behind, riding inside a localized bubble of warped space that itself moves at superluminal speed while the ship inside remains perfectly stationary relative to its own local bubble. Here's the fact that should genuinely bother you. The math checks out, which is precisely why the concept is taken more seriously by physicists than most other faster than light proposals, but the known requirements involve exotic matter with negative energy density, a form of matter that has only ever been demonstrated in vanishingly tiny, fleeting quantum experiments, never in anything close to the quantity or stability the drive would require. Some researchers have proposed refined versions requiring less exotic matter than Alcubierre's original design, gradually chipping away at the most implausible requirements over the past 3 decades. But a genuinely buildable version remains, by most physicists' own admission, either centuries away or permanently impossible, depending entirely on whether stable exotic matter in bulk turns out to exist in the universe at all. The interstellar dust problem. Here's a hazard worth understanding before we reach the most exotic entries, because it quietly threatens almost everything on this list, regardless of which propulsion method eventually wins. Interstellar space isn't perfectly empty. It contains a thin scattering of dust and gas, drifting particles usually no larger than a grain of sand, sometimes smaller. At the speeds proposed for advanced interstellar travel, even a fraction of the speed of light, a collision with a single dust grain stops being a minor nuisance and becomes a serious engineering threat. Here's the fact that should genuinely bother you. At 20% of the speed of light, the kinetic energy released by a spacecraft striking even a millimeter-sized dust particle is comparable to a small explosive detonating directly on the hull, and over a multi-year journey, a spacecraft would statistically expect to encounter a meaningful number of such impacts. Proposed solutions include thick forward shielding, deliberately vaporizing incoming dust with a forward-facing laser or plasma field before impact, or simply accepting a gradual cumulative erosion of the leading surface across the entire voyage. Here's the part that lingers. This single unglamorous hazard, essentially cosmic gravel, is treated by mission designers as seriously as the propulsion problem itself, because reaching another star system only to have the hull fail from accumulated micro impacts partway through the journey would make the propulsion breakthrough that got you there completely irrelevant. Generation ships. Here's the fact that reframes this entire problem one last time. What if the engineering challenge isn't actually the bottleneck at all? What if it's the human lifespan? A generation ship is a proposed solution that sidesteps every propulsion limit above by simply accepting a multi century journey and building a self sustaining, closed loop habitat large enough to support an entire community of people living, growing food, raising children, and dying aboard the ship across dozens of successive generations, with only the many times great grandchildren of the original crew ever actually arriving at the destination. Here's the fact that should genuinely bother you. This isn't primarily a propulsion problem anymore. It's a sociological and ecological one, requiring a closed biological life support system stable enough to run essentially forever with zero resupply, and a human culture stable enough to maintain the mission's original purpose and technical knowledge across a span of time longer than most nations in human history have managed to stay intact. Every proposed generation ship design has to solve for genetic diversity in a limited founding population, psychological stability across generations who never chose to be born on a ship, and mechanical systems that must not fail even once in centuries of continuous operation. Here's the part that lingers. Of every method on this list, a generation ship is, in some ways, the least technologically demanding. It could theoretically be built using something close to today's propulsion technology, and yet many mission planners consider it the least likely to actually succeed because keeping a closed human society intact and functional for centuries has never been done, anywhere, even once, under conditions far less demanding than deep space. Let's sort these eight again a different way, not by how exotic the physics is, but by how long the actual trip would take. On the practically never end, chemical and ion propulsion, both incapable of reaching another star system within any human timescale at all. On the multi-millennia end, nuclear thermal propulsion, an improvement, but still measured in tens of thousands of years for any meaningful interstellar distance. On the single career end, nuclear pulse and fusion propulsion, both capable, on paper, of reaching a nearby star within 50 to 100 years, long but within reach of institutional multi generational planning. On the fastest currently conceivable for cargo end, beamed propulsion, capable of reaching Alpha Centauri in about 20 years, but only for objects too small to carry a person. And on the mathematically permitted but unbuildable end, antimatter propulsion and the Alcubierre warp drive, both consistent with known physics, and both blocked by engineering and material requirements so extreme that neither has a credible construction timeline at all. It's worth remembering before we close that reaching another star and communicating with another star are two entirely separate problems, and we've already solved a version of the second one badly. Radio signals travel at the speed of light, meaning a message sent toward Alpha Centauri today would take just over 4 years to arrive, and any reply would take another 4 years to return, a 9 year round trip for a single exchange, achievable with current technology, no propulsion breakthrough required at all. Every propulsion method on this list exists specifically because a message isn't the same as a person or even a physical probe. You can send information to the stars today, slowly, and get an answer within a decade if anyone happens to be listening back. Sending anything with mass, especially anything alive, is the problem this entire list has been trying, and mostly failing, to solve. Here's the last thing worth sitting with. Every method on this list is bound by the same unforgiving arithmetic. The nearest star is so far away that fast and far only reconcile through either enormous patience, energy sources humanity hasn't mastered yet, or physics so exotic it borders on speculation. We have, right now, only ever sent chemical rockets past our own solar system's edge, moving so slowly that reaching the very next star would outlast every human civilization that has ever existed. Everything else on this list is a bet on which future breakthrough arrives first, and right now, nobody actually knows which one that will be. Not bad for stick figures on a rock,